Hello everyone. So now I'm going to demonstrate to you and how do we derive the magnetic boundary conditions. So let's assume we have this interface or a boundary which split the two different regions. Let's say the first one here I have my first region and down here I have my second region. Okay, let's say the B field that propagate within the first region in that directions. Let's say this is our B1 vector, and then the second region it has the B2 that flow or propagate in that directions. Okay guys, so that's our initial assumption how we can derive the magnetic boundary conditions. So again, as we learned previously, so the magnetic or the any vector guys, regardless magnetic or electric, they must have two main different components, where we can simply decompose the vector here B22 is equal to the first one here, our B2 tangential, and also we can have the other component up there, which is our B2 normal component. And likewise guys, for the case of B1 up there, it has also two different main components. The first one we have here, the B1 tangential component, and then the other one here is our B1 normal component. Okay, so we are going to find the relationship between these two components. So let's say we have here the B1, which can be decomposed into two as shown in the diagram, is equal to B1 normal plus B1 tangential, and we do also have the B2 vector, which can be decomposed into two main components, which are the first one, the B2 normal plus B2 tangential. Okay guys, we are going to find the relationship between these two, this B1 normal and this B2 normal, how they can be related to each other. That's our task, and we are going to find the relationship between the B1T and also the B2T. Okay guys, so that's our task now. So how do we find the relationship between these two components? All right, for the case of B1N and B2N, okay, so to find the equation that relate between B1N and also the B2N guys, so we can simply use our fourth Maxwell equations, which can be expressed as here, the closed integrations, the B dot ds is equal to the 0. Okay guys, this is our fourth Maxwell equations in terms of integral, or you can simply put in terms of point form, given as divergence of B is equal to 0. Okay guys, so since guys we are dealing with surface here, right? So by right we can simply draw our Gaussian surface that can be represented or can represent our this expressions of Maxwell equations. So let's focus on this form. So let's say this is our boundary, let's say, and then let's say this is our axis y, and up here z, and for sure guys the x will point out with a dot, right? That's how we draw our axis. So now along here is y axis, and then normal to this z axis, and the x is pointing out of page, so just a dot. Alright, now so since we have this fourth Maxwell equation, so we have to have the Gaussian surface which must be closed So let's say I draw a cylindrical structure. So let's say that's my Gaussian surface. You can choose any other surface, up to you. But now I'm going to choose this cylindrical structure. It's much easier because I have to deal only 3 surfaces, easy. So let's say this Gaussian surface has the length or height is equal to h. Let's say. Okay guys, so this is our first region as defined earlier, right? And then down here is our second region. Okay guys, so based on this simple diagram, you can see that the B1N actually pointing up in positive Z, and also for the B2T pointing up also in positive Z direction. So you can simply draw our B1N and B2N as shown here. That's going to be our B1N, belong to first region, and down here again in the same directions but different value or magnitude. Here it belongs to B2 normal. Okay guys, right, so let's expand this integral. Since we have 3 different surfaces, we have top surface, bottom and side, so we must have at least 3 different integration paths as shown here. So the first one here, we're going to have the B dot ds number 1. As I define, the first here is our first surface, and the top and the down and the bottom here is our second surface, and then the side surface become our third surface. That's my assumption. And again, proceed to the second one, integrations, the B dot ds number 2 for the bottom surface, and then plus the B guys dot ds number 3 for the side surface. Alright, so that's our complete expressions of these Maxwell equations, and now must equal to 0. Okay guys, so let's look at carefully for the first surface here, right? The first surface actually focusing on the top surface that I show you here. So at this figures, the only B that appear actually B1N, isn't it? So here we can simply change to B1N that actually pointing or propagate in positive Z. So you can simply put here Z directions. Okay, and again guys, the ds here, as we learned last time, I remind you many times, the ds vector must always point away from surface. So but guys, for this particular surface, the ds here actually in positive Z direction because it must point away. So now the ds number 1 here for the top surface equal to the Z ds. Okay, it must point away from surface, so that should be your ds number 1 direction up. Okay guys, so let's look at to the next surface over here. Now we are going to look at to the bottom surface. If you look at carefully guys, the B here for the down here, the only B that exists actually the B2N, isn't it? Because at this bottom surface, the only B that only is actually B2N. So now again B2N guys point in positive Z, so you can simply put here positive Z directions. Okay, and now again now for the ds number 2 here guys, again I mentioned here the ds must always point away from surface. So since surface is down here, so the ds number 2 should be downwards, right? So that should be ds number 2 directions. So you can simply here put a negative Z ds. Okay, and here is our positive as ds number 1 upwards, and ds number 2 is downwards. Okay, okay guys, so the next part is our third integration part for the third surface on the side surface of this cylindrical or Gaussian surface. Now guys, for this case guys, for the side view, we know that there is 2B axis, which is from here to here the B2N axis, and from here to here B1N axis. So the B here guys actually composed of two different B, which is B1N and also B2N, but yet both of them pointing in same positive Z directions. Okay, so again I repeat, so for this third integration, so the B that exists for this side surface, actually they have two B components. The first one B2N, which exists from this limit to this boundary, and then B1N, which exists from this boundary to the last limit. Okay, so that's why we have two B normal, okay, B1 and B2. And guys, the DS2 here actually refer to the surface area of the side of cylinder, and again it must point away from cylinder. So the DS here guys can simply change to the positive R ds. Okay guys, so if you do dot product between B and ds, you can see here from here Z dot Z, yes we have this value. Z dot minus Z, yes we have this value, but now we have Z dot R, so we don't have this value anymore, it will be 0, because dot product between Z dot R 0, right? The output, the result of that operations of the product. So now let's proceed to this two part of integrations. So now we do have the B1 normal area minus the B2 normal area is equal to 0. So let's simplify. You can find this final equation equal to B1N, which equal to the B2N, or you can simply put vector because they are same. So guys, this is our first normal equations that we derive from our fourth Maxwell equations. Okay, that's our normal boundary equations. Right guys, okay, so that's the first part of derivations. I have shown you how we can derive the normal boundary equation from our fourth Maxwell equations in terms of integral. Now we are going to proceed the derivations to find the tangential component equations. Okay guys, so let's proceed. Hello everyone. Okay, let's summarize what we have learned during our live class last time. We know that due to the magnetization process, there will be two different current density will appear on the magnetic material. So the first one, we know that the JSM, actually our magnetization surface current density, which equal to this M vector cross AN. So this one is our, again, magnetization surface current density. And we do also have the second one that appear on the magnetic material when they are being exposed to the H or B field, which only exists within the material, which is here we have the JM. JM here actually guys, the magnetization volume current density, which equal to the curl of M. M here is our magnetization vector, right? So M here, our magnetization vector. Magnetization vector. Okay guys, so now let's do comparison between the case of free space and also the case of magnetic material. So let's say the case of free space, we have here from our third Maxwell equations, given as the curl of H is equal to J. Okay, this is a case of free space. So the H here can be expressed also in B term, given as the curl of B over mu naught, because of case of free space is equal to the J. The J here is also our volume current density. Okay guys, this is a case of free space. Right, so if we proceed to the next part, now we're going to write down the related equations that actually valid for the case of magnetic material. So now the second case here, case of magnetic material. So again, using the same third Maxwell equation in terms of point form as shown here. So that's going to be our equation of Maxwell. So curl of H, guys, and equal to the J. But guys, for this case, we have additional J, which we have discussed earlier up there. So this is actually the case, the volume current that exists within the magnetic material when they are being exposed to the H field. So now we have to add up this factor of Jm. So now we do have this term of Jm. Okay guys, so make sure we know that this actually our volume current density, and this is our magnetization volume current density, which only exists within magnetic material. Okay guys, so we know that, guys, the Gm here is equal to this curl of M. So we can simply change this Gm equal to curl of M, whereby we can bring this term to the left and factorize with this H. So we do have and we also can change the H, guys, into this term B to equal over mu naught. So now we have the curl of B over mu naught for this H, and then after we bring this term over here become negative, so now we have a negative curl M, right? And now it's equal to the J. Alright, so now let's do comparison between the first term up there and then with the last term down here. Okay, guys, so what will you see? So we can check the similarity. We do have here curl operator. Yes, curl operator. We do have the J and the J here, and now we do have this H, which equal to this whole term here. So let's put this expression, the H is equal to the B over mu naught minus M. Right guys, so let's combine the H to the M, and I just want to find the B only now. So the B here is equal to the mu naught H plus M. Okay guys, so we also know that the M here, guys, actually is equal. If you can express the M in terms of H, yes, we can do that by replacing the M here is equal to the psi M H, whereby this psi M is actually referred to the magnetic susceptibility. Right, let me get down here. Magnetic susceptibility. Alright, so let's put this conversions of M. Now we do have here mu naught, and let's factorize the H as well. Now we have 1 plus psi M H. Okay guys, so let's define, guys, this expression is equal to the mu R. Now we do have the final expression of B here equal to the mu naught mu r h, whereby this mu r actually refer to our relative permeability. Relative permeability, or we can also simplify the expression the B, which equal to the B equal to the mu h that we always see right before. So how do we convert this B to H or H to B? So this is the relationship between these two parameters. Okay guys, so now we do know already the JSM is equal to M cross AN. We also know that the JM is curl of M, and now we do have these expressions of B and H, which equal to mu naught mu r, and we also know that the M here is equal to the psi m h, whereby the psi m here is refers to the magnetic susceptibility. Okay guys, so let's do one example that has a relationship between these equations. So let's turn to page 381. Page 381 of practice exercise 8.7. Okay, so here we have in a certain region given to us, the mu equal to 4.6 mu naught. Right, let's say in certain regions. So we are given this information. So we do know that, guys, this 4.6 based from previous explanation will be equal or refer to your relative permeability. Alright, and then we also have the value of B, the magnetic field density, given as 10 exponential minus 7 in Z directions milli-Tesla. Okay, so that's our exponential minus y. Okay, here is our y. Sorry for that. So now we are going to find the first one, actually looking for the psi m, our magnetic susceptibility. So based on previous discussion just now, we know that the 1 plus psi m is equal to our mu r, our relative permeability. So we can find the psi m by just rearrange this equation. So we're going to have here mu r minus 1, and this our mu r is equal to 4.6. So we're going to have finally 4.6 minus 1, which is equal to 3.6. Okay guys, this is our magnetic susceptibility for this particular material. Okay, so now we are going to find the H. The H, okay guys, the H can be obtained from this simple equation. The B is equal to mu H, so I can simply find the H just by rearranging this equation, the B over mu, and we should know that, guys, this mu actually belongs to mu r mu naught as shown up here. So let's put the value of B as given up here. So that's our 10 exponential minus y in Z directions milli-Tesla, and then over its mu equal to 4.6 mu naught. Alright, so if you proceed, you will find the value of H, which equal to 1730 exponential minus y. Again, they must have in the same direction, in Z directions, and now it has unit of ampere per meter for the case of H field. Alright guys, so now I want to find the M vector, or our magnetization vector, the M. Okay, as we discussed earlier just now, the M can be related to the H field by applying this simple equation. The M is equal to psi M H. Psi M H is actually our magnetic susceptibility as obtained earlier, 3.6. So just times here 3.6 and times the whole term there. You have here 1730 exponential minus y. And again guys, they must have same direction because the M and H is directly proportional. So you're gonna have here Z over, so that's all. Then now the M must have same unit of H, which equal to the ampere per meter. So finally gonna have here the M vector, which equal to 6228 exponential minus y. Again, same direction of H in Z directions, and it must have same unit with H, ampere per meter. Okay guys, so I hope you can try yourself and make sure you are familiar with all these terms, the M, the psi M, and also the mu R, and also for the previous one that we have earlier, the JSM, and also for the JM. Okay guys, so and all the best for your study. Okay, thank you.